Welcome to our presentation on normalization and ERDs. We are Group 3, and our group members are Jeremy Meyerson, Alex Martinez, Elizabeth Smith, and Taylor Harbin. Okay, so we want to start off this presentation by giving a little refresher on some important terms and also giving a brief history of how it was created. So to begin, a key is a value used to identify records in a table uniquely and helps establish a relationship between multiple tables in a database. Primary keys are a single column value used to uniquely identify each record in a table. Every time a new record is inserted, the primary key must be given a value. Finally, they cannot be left null, as you will see in our example coming up. A foreign key is similar, but they do not have to be unique and can also be left null. A composite key is basically just multiple primary keys grouped together in their own table. So a little history of how it was created. In 1970, an IBM employee named Edgar F. Codd was a mathematician that worked in the San Jose Research Lab. He published a document explaining how information is structured and stored in large databases. He was able to figure out how the data is retrieved and stored and thought about ways that the data was related. Edgar F. Codd was the first to define first normal form in 1970 and then second and third normal form in 1971. Today, we define normalization as a process of reorganizing data so that it meets two basic requirements. The first one is that there is no redundancy of data and all the data is stored only in one place. The second is that data dependencies are logical and all related data items are stored together. Normalization was created to organize data in databases to avoid redundancy and reduce errors. When a data set is normalized correctly, it minimizes the risk for errors and update anomalies. It also allows us to use the minimum disk space to be utilized within the database, which in turn increases efficiency. So we thought the best way to demonstrate the process of normalization was by walking you through an example. The example shown here is sales records for a mobile phone store. It includes the customer's name, address, and preferred magazine. It also includes the supplier of the phone, their phone number, and the price of the device. This data set is currently unnormalized, and this business would have a difficult time referencing, updating, or adding to this list. So right off the bat, you can see, if you look at this table, that there are two Bob Smiths, and it's not really clear how to distinguish them. Second, Evan Porter, he looks like he purchased two items here. Third, you can notice that his supplier and supplier phone are wholesale and toll-free, which looks a little bit different from these other data types. So we're going to look to address these through the process of normalization. So these are the rules for achieving first normal form. They state that every column in a table must be unique. Separate data tables must be created for each set of related data. Each table must be identified with a unique column called a primary key. No rows or columns contain null values. And finally, no rows or columns contain multi-valued fields. So this is first normal form here in this table, and the first thing that we addressed was the fact that Evan Porter made two purchases. We fixed this by splitting it into two different rows so we can better reference that sale. And also you notice that in the previous example, his supplier and supplier phone weren't like the others, so we changed it to the according values. And lastly, we created a primary key field called customer ID, so that way the two Bob Smiths have their own unique username. Many businesses require the data to be further normalized in order to use it in their applications. Second normal form is based on the concept of full functional dependency. In other words, every non-primary key attribute is fully functional dependent on the primary key. The data must first meet the standards of first normal form, and then we must split all the data up that results in many-to-many relationships and store that data in a separate table. Another solution might be to introduce foreign keys. As we stated before, a foreign key is a column or group of columns in a relational database that provides a link between two or more data sets. So as we continue with our example, this is second normal form, and we first begin by splitting the data into two data sets. The first one contains the customer's ID, their name, shipping address, and preferred magazine. The second table over here contains the item they purchased, the supplier's phone number, and the price of the item. Imagine if we needed to change the phone numbers for one of these suppliers. If it was unnormalized, or even in the first normal form like before, we would have to update this value in several different places, which would take time and waste resources. Instead, we have a separate table for the items which we can easily update or even add new items in the future. We have selected the customer ID and items as primary keys, and they're seen down below in their own table. This is an example of a composite table which we defined before. This second normal form makes it a lot easier to reference the data and transactions that each customer made. This brings us to third normal form, which is the final form we will be discussing in this presentation. This level of normalization is considered adequate for normal relational database design because they are free of insertion, update, and deletion anomalies. In order to achieve third normal form, the data must meet the standards of second normal form, just like before, and the tables must also have no transitive functional dependencies within each other. A transitive functional dependency is an indirect relationship between values in the same table that causes a dependency between them. In order to eliminate these, you must make sure that all the fields can be determined only by the key in the table and no other column. The final step in normalizing this data set was to split up the supplier table. Notice we have identified the supplier as a foreign key and created its own separate table for it. Supplier now becomes its own primary key in this table, and it becomes more easily updatable in the future. This table allows us to easily add new items and suppliers down the road if our business decides to expand.
Now moving on to entity relationship diagrams. Now, what exactly is an ERD, aka an entity relationship diagram? Well, they are a visual method of depicting the relationships between the various entities that comprise a relational data system. The concept of the ERD as we know it today first emerged with Dr. Peter Chen in 1973, who viewed ERDs as a potentially helpful tool to conceptually model data systems before their deployment. This would ultimately be validated, as the visual analytical tool they provided minimized errors and helped ensure effective normalization to the third normal form in the logical design of databases. In fact, the creation of ERDs prior to relational DBMS deployment is now considered an industry-wide best practice. Additionally, ERDs have proven equally important for modeling existing relational DBMSs, both with regards to proper maintenance and overhauls or modifications. In order to understand why ERDs are so fundamental to relational DBMSs, we must first consider a typical ERDs. ERDs are generally composed of three primary components: the entities, represented in this diagram by these two rectangles, their attributes, represented by these two ovals, and their relationships, represented by these two diamonds. And we will talk about these types in a second. Starting with the entities. An entity refers to any object, such as a person, place, thing, product, whatever, which we are attempting to collect and maintain data around. Entities do not have to be physically tangible objects. However, they do need to be clearly defined and recognizable within the observed environment the DBMS is modeling. Entities can take on two forms: strong, aka normal entities, and weak entities. To illustrate these concepts in a novel way, let's consider each person a normal entity who is defined by a unique last name. You may have a dating couple where both partners are unique normal entities in this system. However, say if this couple were to get married and one partner takes the last name of the other partner, the one who has taken their spouse's last name is now a weak entity. This is because they are still a unique identifiable person, but they are now defined by the primary key, specifically the last name, of a weakly related normal entity, in this case their spouse. This example works well for illustrating these concepts. However, in an actual DBMS, it would be incredibly computationally expensive to have every single person that exists modeled as a unique separate entity in their own table. Thus, we often create tables with entity sets composed of many normal and weak entities, with weak entities identified by composite keys of their initial value usually, and then the value that they are now being identified by, so as to create a grouping for various entities of the same nature. Thus, at KSU, our students are all distinct entities who are grouped within the larger entity set of KSU students. And if a KSU student were, say, to get married and take their spouse's name in our example, then they would likely be identified by a concatenation of their original last name and then the new last name of their spouse, continuing that example. Now, within these entity sets, each entity will then have various attributes that describe their relevant features. For example, in the entity set of KSU students, there will be attributes describing the students' names, their phone numbers, their email addresses, as this is all important and relevant info concerning these students. There are 4 types of attributes that we would use to store this data, with the simplest one being the simple attribute. The simple attribute is one that has a data value that cannot be further broken down into any meaningful data, leading some to refer to this as an atomic value. For example, if there is an attribute for a student's GPA with a value of 3.0, there is nothing to be gained from solely looking at the 3, the period, or the 0 by itself that cannot be gained from looking at the 3.0 as its full value. Next, we have composite attributes. As we previously discussed, these are attributes which contain a composite data value, which is often compiled by concatenating together 2 related values. As another example, if there's an attribute for a student's full name, this is a composite attribute, as it is the composite of their first, middle, and last name, and can be broken down further into these simple attributes. Next, we have derived attributes. These are attributes which, like their name suggests, are not explicitly listed as attributes in the dataset, but are rather derived from them for insight. An easy example of this is if there is an attribute for a student's date of birth. This can then be used to get the derived attribute of the student's current age. And finally, there are multi-value attributes. These are attributes which, also like their name implies, can have multiple values for a single entity. For example, a student may have multiple different phone numbers recorded, making their phone number a multi-valued attribute. And we can see from this helpful diagram how these attributes would be represented in one ERD modeling method. So you can see we have our just standard attribute, one that is a primary key, one that is a partial key attribute. Then we have our derived one by this dashed line, our multi-valued indicated by the contained ellipses, and then finally our composite. Next, let's move on to the relationships in an ERD. Generally, relationships are described in terms of their cardinality and optionality. Cardinality refers to the quantitative roles of each party in a relationship, and optionality refers to whether these roles are mandatory or simply voluntary or optional. In a nutshell, this essentially describes how many times each party can be involved in the defined relationship and whether they have to be involved in the first place. The 4 cardinalities we'll discuss are one-to-one, one-to-many, many-to-one, and many-to-many. And we will get into an example later that further shows these, but the symbols that are associated with mandatory and optional one or many, as you can see, for mandatory one, we have these 2 solid lines. For a mandatory many, we have 1 solid line, and then the spreading out lines. For an optional one, we have 1 solid line, and then our circle. And then for an optional many, we have our circle, and then our spread out lines. So now, in order to explain these cardinality and optionality combinations in relationships, we have prepared multiple examples on relatable topics. Firstly, the relationship between a KSU student and paying tuition is an obvious example of a mandatory one-to-one relationship, as each KSU student must pay their singular tuition and no one else's tuition but theirs to attend KSU as an individual student per semester. On the flip side, a KSU student signing up for the dining plan on campus is an optional one-to-one relationship, as they are not required to buy a dining plan to attend, but if they do purchase a dining plan, it is only for that specific individual student, and it will only be useful for eating from the KSU dining facility whenever the student chooses to. Next, for a typical KSU student, their class schedule represents a one-to-many relationship, as there is only one student, yet they can take many classes simultaneously if they so choose. Yet, they do not have to take any classes in a semester if they are unwilling. They can cease being students. Next, each KSU student is assigned one or more specific academic advisors in a mandatory many-to-one relationship, as each KSU student must have at least one advisor, but may have more than one. For example, as an IS student, I believe we have 3 advisors we can choose from. Conversely, the extracurriculars at KSU represent an optional many-to-one relationship, as many students may join a specific extracurricular activity, but they are not required to. And finally, the relationship between KSU students and the parking spots at Central Parking Deck represent a many-to-many relationship, as many students, in my opinion too many students, may park in many parking spots. If we understand all of these components, let's run through the steps of making an ERD and create a mock ERD about KSU students. Before beginning, we will just quickly go over these steps and then show them in practice. So the first step, identifying the entities. The second step is identifying the relationships. The third step is identifying their cardinality. The fourth step is identifying the relevant attributes we want to model. And then the fifth step is creating the ERD. Now for the first step, we have to identify all of our entities. For our scenario, we decided to be modeling the average scenario of interaction between KSU students, the advisors, the faculty departments the advisors are in, the professors at KSU, the classes that they teach, and the courses that those classes are teaching. Next, now that we have identified these entities, let's identify the relationships. So, a KSU student is advised by an advisor. There's a clear relationship. That advisor is part of a KSU department. Similarly, a KSU professor is also part of a KSU department. That department will have courses, and then those courses are divided into class sections. A KSU student can take classes in these sections, and a professor can teach these sections. Now we must identify their cardinality and optionality. So, for a KSU student being advised by an advisor, many students, at least one, will be advised, and each student will have at least one, but potentially more advisors that they can get advising from. For example, as an IS student, I believe we have over 2 advisors that are available to us. Branching off from the advisors, at least one, but likely many advisors, will be in each department that is relevant for them in terms of KSU departments. We have information systems advisors, accounting and business advisors, arts advisors, etc. Similarly, we'll have at least one, but many, as we know, professors at KSU who are part of departments. And there can only be, for the sake of our diagram, we decided that each advisor and professor is only part of one department because we don't know how they've arranged it at KSU, but it might be, they can be multi-department, but regardless. Moving on from our departments, each department will have multiple courses that they teach. For example, we are in the capstone course for the information systems department. These courses that are offered by each department are then broken down into class schedules. So each specific individual course will have multiple class sections that are available, at least one, although sometimes, KSU fails at that, but in an ideal world, at least one, but likely many. Likewise, each class will only have one professor, but they can teach at least one or as many classes as they feel like. And finally, a student, there are many students, but there's at least one, or we don't have a university, can take at least one or up to many classes, depending on how they feel. And for this sake, we decided that, if you're not taking a class, you're not really a student. So that was our approach. And now, using the shapes that we demonstrated before, we decided to break down the KSU advisor and KSU student relationship into this relationship, just showing, we have one-to-many students that are advised by one-to-many advisors. Now that we've identified the relationships and their cardinality, we had to identify the relevant attributes. So for the sake of brevity, we won't go over every single one of these. But for example, we created a primary key, a student ID, that each student is uniquely identified by. And then, we decided that maybe their first name and last name, their phone numbers, their email address, etc. would be useful attributes that the school would want to know. Likewise, you can see that we have various foreign keys around to relate some of our related entities to the others by their attributes. So you can see each course has their department ID that the course is from as a foreign key, So that way we can maintain normal form, but you can, very easily relate it and say, this capstone 4880 class is for the IS department, proving the usefulness of that. And for example, you can also see in our KSU classes, we created a composite primary key because, we can't use just the course ID because there might be many class sections, and we can't just use the professor ID as the professor might teach many different distinct classes. So by combining the course ID and the professor ID, we can create a composite key that very easily identifies each unique class section. And finally, we need to create the ERD. And now we personally used Lucidchart. However, Microsoft Office programs such as Visio and PowerPoint are common choices for modeling ERDs. There's also other softwares such as Glyphy that offer tools for modeling ERDs. Furthermore, some may even choose to draw out ERDs by hand on paper or whiteboard to ensure a more collective and communal approach to development. However, one very useful approach that is gaining popularity is utilizing scripting to auto-generate ERDs for datasets. By utilizing scripting tools, such as Microsoft PowerShell, one is able to create scripts that will pull from a dataset in a relational DBMS, such as Microsoft SQL Server Management Studio, and configure an ERD, whether as an HTML object, a Visio sheet, or whatever you so code, with the latest, most relevant data you chose to pull. And additionally, many relational DBMSs have native tools for creating entity relationship diagrams already, such as Microsoft SQL Server Management Studio's database diagram option, or MySQL's Workbench's reverse engineer option. So if we had this data right here in a Microsoft SQL Server database, we could then actually, press the database diagram option and instantly generate this without having to spend, an hour in Lucidchart how we did. So that's a very useful way to do that. And, just showing here very quickly, our primary keys, our multi-valued attributes on the student, So in conclusion, thanks for watching our presentation. Now you are ready to begin normalizing data and creating ERDs. Thank you.